Alrighty. Today we'll be talking about fossil fuel technologies. Um, Last class, we had an overview of the pathways from which you go from, your primary fuel to end use, and so, maybe going from coal to electricity that you use at home. And so today we'll be covering basically what happens in between from a physical and engineering standpoint. Okay, and so fossil fuels. So fossil fuels are formed by decomposition of dead organisms, so they really are literally fossils. So exposure to heat and pressure basically causes chemical reactions that results in the formation of these three sort of most common fuels. So petroleum, also known as crude oil, natural gas, and coal. These are, again, as mentioned last time, kind of like the most prevalent forms in each state of matter. So you've got liquid petroleum, gaseous natural gas, and solid coal. And we'll be talking about some of the details of the compositions of actually these materials. So coal, for example, can take the form of lignite, bituminous, or anthracite. The way I like to sort of memorize the breakdown is L in lignite is for low grade, bituminous, B for B grade, and anthracite or A grade. And that kind of refers to the relative energy density and purity of the carbon composition in the coal. And so with the higher grade ones, you're usually getting quite a bit more energy. So in a later lecture, we're going to talk about fossil fuels used in transportation, but today we're going to be focused on electricity generation, and so we're mainly going to be dealing with coal and natural gas. So the chemistry for these two compounds is very quite different. So on the left side is kind of like a typical sort of example of a chemical composition of some piece of coal, and coal in general doesn't all sort of look exactly like this, but the structural form is sort of well characterized by all these benzene rings. You've got a lot of impurities usually. So here you can see there's sulfur and nitrogen contained within here. And yeah, and so from a combustion perspective, which we'll talk about in a second, you'll notice that coal releases lots of non-carbon byproducts. That's compared to natural gas, which is just methane, CH4. It's a very sort of simple compound, especially compared to coal, but the extraction of this fossil fuel also includes lots of other impurities sort of listed here. So just because it looks like this doesn't mean it's a super clean fuel. Okay, and as I was mentioning about the energy density of your different classes of coal, you got lignite, subbituminous, bituminous, and anthracite. And you can see sort of as you go from the lowest grade all the way up to the highest, you can have quite a large variation in the energy density. If you'll notice, like anthracite has almost double, if not more, the energy density of lower grade coal. And so there can be a pretty substantial difference in the types of coals that are being burned at a power plant and the sort of energy that you can get out of them. The United States is actually one of the best places for getting high grade coal. So there are a lot of anthracite and bituminous coal mines in the United States. And that's why for a fairly long period of time, coal was sort of the dominant form factor for electricity generation in the US. Natural gas is measured a little bit differently, right? Because it is in a gaseous form. And as I mentioned before, when we were talking about BTUs, natural gas is around about 1,000 BTUs per cubic feet. And depending on the purity and density of the gas, you can have slightly lower or slightly higher energy content. Total reserves. So reserves kind of refer to the total amount that's available for us to mine and extract. Reserves themselves can be kind of a complex subject, and in fact, reserves can change as more information is and newer technologies are discovered. But right now, the approximate reserves for these fossil fuels are about 1.1 trillion tons or 33,000 exajoules. And for natural gas, it's about 205 trillion cubic meters or 7,600 exajoules. And worldwide annual primary energy consumption is 500 exajoules. So you can kind of do the math where you divide total reserves by the annual energy consumption to get a high level sense of how much longer the reserves will last. And actually, I found a nice little chart about that. So here, you can see the gas and coal reserves compared to annual global energy consumption. This also shows some of the renewable reserves, and right, because they are renewable, they don't actually run out, or at least they're not going to run out anytime soon. So you can see annually how much solar, wind, and hydro energy is available to us. Obviously, with the caveat that it wouldn't be really physically possible or feasible to capture all of that energy. But that gives you a sense of the relative energy versus the reserves compared to the energy consumption. Okay, so let's talk a little bit about the process for fuel extraction, basics of coal mining. There are a number of different types of mines, and this is a nice little graphic showing basically underground mining methods versus surface mining methods. It involves essentially digging into different contours and land surfaces to get at mines that contain your coal beds, right? And so basically, these types of mines are applied to different geographies in order to extract the fuel from its resting location. Most of them, you'll notice that the coal beds are sort of located in these striations horizontally, and so oftentimes you're sort of digging horizontally through the land in order to get at the resources. It can result in a lot of environmental damages. So this is a picture of a specific type of mining called strip mining. And you can see this particular tract of land as a sort of before and after. And so the local impacts can be quite severe. For natural gas, this is a more sort of conventional extraction of natural gas, where you are able to essentially, in this left one here, you can essentially drill straight down into a pocket of gas and extract all of it. And that type of footprint is actually quite a bit smaller, but can lead to different sorts of environmental damages. And more recently, you guys may have heard of a technique called fracking. That is also known as unconventional resources. And that has led to a actually fairly large increase in the reserves for natural gas, in that we now are able to tap into a larger pool of resources than before. And so the fracking process is quite a bit different. So on the right side, you can see here, you drill down, but then you actually have these horizontal drills that go through essentially a shale, a section of shale, and you have high pressure water that basically fills into all of the gaps and pushes out the natural gas. And so this technique is actually fairly modern, sort of developed in the late 2000s, and that led to a lot of actually pretty big changes in the electricity grid sector, and we'll get to that in a little bit. But this technique uses quite a bit of water, and that wastewater has to be recovered, and it actually, a lot of it is basically unusable, and it's not really economic to clean it. So oftentimes they're just kind of sitting in water recovery tanks. There were initially some issues where it might flow into the local water table, and that kind of contamination is extremely harmful for the environment because it basically pollutes the entire water table. You may have seen, and if not, you should YouTube this, videos of people who basically are able to light the water coming out of their faucets on fire. And that's because the leaks into the water table lead to high concentrations of methane contained within the water. So it's actually like flammable water. The US has, in terms of the shale resources, a very large sort of reserve of shale resources, which led to an explosion in fracking in the last like 15 years. And that has led to a sort of big transition towards the use of natural gas compared to coal. Here we can see sort of since the late 2000s, the average price of coal versus natural gas spot prices. And what you can see here is that sort of a sort of trending upwards price really led to, or once fracking became more widespread, the prices of natural gas really sort of dropped quite a bit. And so that led to a big shift in the provision of electric power from natural gas compared to coal, basically due to the economics and the relative cheap price of natural gas. And actually when it's kind of interesting, A lot of environmental groups sort of decry fracking in general, which is a totally fair argument, right? There are a lot of environmental damages associated with that, and we are still using a fossil fuel, but the switch from coal to natural gas has led to a larger carbon emissions reduction in the U.S. economy as a whole, and that reduction is larger than any other sort of public policy or technology transition that has happened in the last decade, because you've shifted so much coal to natural gas, and natural gas is about half as carbon intensive per unit of electricity generated compared to coal. And so, yeah, fracking definitely introduced a lot of problems, but overall, I think the benefit in terms of GHGs is often understated. Okay, so then once you've extracted the resources, there are some processing steps. For coal, basically all of the processing happens at the plant. So you've got these big, essentially freight trains that are carrying hundreds of train cars filled with coal. They arrive at the plant and sort of dump them out into this process where it has a little bit of filtering, but mainly to remove like scrap that's not really combustible. And then all of that fuel goes through a number of like crushers and millers that will grind the coal down into like fine particles for combustion. Okay, and the reason why you do that is it makes for more efficient combustion, because the finer the particles, the more surface area you have to work with for the combustion process. For natural gas, it's quite a bit different. So as I was mentioning before, there are a lot of impurities, right? So you've got it in the sort of high pressure fracking fluid. You've got a whole bunch of stuff in there. You've got oil, you've got water, you've got a bunch of impurities. And so that material will go through a processing plant to try and remove as much non-hydrocarbons as possible. And then all of that will output out as sort of the end thing that you want, the natural gas. It gets compressed and then distributed to whatever sort of the main end use is. Some of that is going to go towards industry and residential and commercial use for, for example, if you're doing gas heating or for cooking on your stovetop. But a whole bunch of the natural gas is going to be going towards power plants for combustion in order to produce electricity. Okay, so the way that we are getting energy from these fuels is through combustion. So generic hydrocarbon chemistry, if you have hydrocarbons with n number of carbons and m hydrogens, you combine that with oxygen to produce CO2, water, and heat. So natural gas combustion is pretty easy to do from like a chemistry perspective, right? You have methane and 2 oxygen molecules will produce a single CO2 and a single molecule of water. But even though the natural gas goes through this sort of long pre-processing step before it gets combusted, you're still going to have impurities in there, right? So the way that the processing happens you could in theory get the methane to be 100% pure or almost 100% pure, but really the amount of processing is dictated by, one, the economics of actually doing it. So you only want to make that natural gas as pure as is sort of economically efficient, and then two, from regulations that are requiring that the combustion process itself is adhering to a specific standard. And so those are going to drive, how pure the methane ends up being after the sort of pre-processing step. And so you tend to get a lot of these byproducts, nitrous oxide, carbon monoxide, carbon dioxide, methane. So I should quickly mention, so the methane byproduct is partly from incomplete combustion, right? So it just happens that some of it escapes, but actually when fracking started to become mainstream, there was a controversial paper published by a professor in Cornell who basically was saying that the emissions impact of methane is much higher than we had originally anticipated and measured from combustion, because in the upstream pre-processing and sort of transportation through pipelines and from transport trucks, you get methane leakage, and that leakage increased the effective emissions over the life cycle by a large factor. And the reason for that, right, is methane as a greenhouse gas is a lot more damaging to the environment than carbon dioxide. And so that actually spawned a sort of large task force from the EPA and a whole bunch of others, scientists who sort of investigated this claim, and it ended up that probably the impacts from that paper were overstated, but that it was an important kind of wake-up call to, one, kind of regulate that, and two, to deal with the leakage issue. And today I kind of assume it's a lot better, although I guess I haven't followed that issue that closely recently. Okay, so and then coal combustion, you'll note that I didn't put a chemical formula here because coal is an absolutely crazy compound. And as we showed before, there are tons and tons of impurities within the solid, and that can result in a whole bunch of byproducts in combustion. So this is just a laundry list of them, but ash, bottom ash, slag, these are all solids that come out of the combustion. And because of that, you end up having to have fairly robust filtration and protocols for ensuring that the pollution coming out of coal plants falls within regulatory requirements. Oftentimes this means, the downtime maintenance and when it's not in operation is resulting in cleaning of a lot of these materials, which can build up pretty quickly. And then basically from gases, all the things that you see in natural gas combustion, you'll see, but because of the higher concentration of things like sulfur and heavy metals, you're going to get a lot more sulfur dioxide, as well as mercury, arsenic, and other metals. Yeah, the sulfur dioxide thing is actually a pretty big deal. And the I believe in the 1970s or 80s, following the Clean Air Act, there were some requirements to reduce sulfur dioxide emissions, and that was a pretty cool thing in the technological development of these sulfur filters that were installed in coal, and actually made a really big difference in reducing things like local acid rain that results from emitting lots of sulfur dioxide into the air. Okay, so how do we extract the energy from this combustion process? Okay, so there are a whole bunch of things called heat engine cycles. And so this is something that you will get into in mechanical engineering a lot more when we're talking about kind of the math behind these things. And I just want to introduce the concept. Actually, most people from last class said that they're coming from engineering backgrounds, so hopefully some of this is going to be familiar, or at least an easy review. But the whole idea of a heat engine cycle is that you can take advantage of a system that goes through like a cyclic process, so that you can sort of continuously be able to exploit a combustion process for energy. So you go from an initial state, you go through a whole bunch of series of other states, and you go back to an initial state, and that's kind of the thermodynamic cycle. And every time you go through the cycle, the system is able to essentially do some work. And you're unfortunately, you know, in that chemical process of doing combustion where you get a bunch of heat, you cannot actually convert all of that heat into work due to the laws of thermodynamics. And so we'll talk kind of briefly about what sorts of cycles are seen in existing power plants today. So the relevant cycles, okay, the first one is more kind of like a theoretical cycle, and that's kind of to get us oriented towards understanding the sort of theoretical maximum that you can really get out of a system, and there isn't going to be anything that kind of resembles that high level of efficiency in practice. So with the other cycles, the Rankine cycle, Otto cycle, and Brayton cycle, these are simplified cycles that actually represent real world thermodynamic cycles that are being used in power plants and engines today. So the Carnot cycle is an upper limit in efficiency that an engine can achieve. It's a theoretical construct because it's kind of a perfect engine, and you can't actually build it in practice. So the way it works is you have this piston that moves up and down, and you have a cold reservoir and a hot reservoir. So from the hot reservoir, you get heat moving into the system, and that leads to this isothermal expansion, which moves the piston, once it cools down, it goes through an adiabatic expansion, which moves the piston upwards. The isothermal compression, which means sort of compression that's happening without changing the temperature, that is caused from when the heat leaves your system into the cold reservoir, and this compression kind of returns you back to your neutral state. And so when we talk about this system from a theoretical perspective, right, there are lots of things that aren't really sort of physically possible in this diagram, right? So this would be like considered to be in a frictionless environment, and that your reservoirs basically don't don't leak any energy besides what's going into your piston system. And so it's, again, not possible to do this, but with this kind of system, you're extracting basically as much of the energy from heat into work as possible. Okay, and so when we think about doing this sort of energy conversion from heat, right, which you're getting through combustion, into kinetic mechanical energy, how is it that we are able to then take that and get it into the form of energy that we want, which is electricity, right? We don't actually have a bunch of like mechanical movement from combustion that gets transferred directly into our lives in a way that we would want it, right? And the basic idea here is that you are able to generate electricity through mechanical energy. And so kind of the big takeaway here is that if you can basically spin a magnet, right, you can produce a magnetic field, and that will lead to the generation of current through a wire. And so you have your two primary components, a rotor and a stator. So I guess the sort of really big takeaway here is that when we think about almost any sort of power source besides, let's say, solar. So when I'm talking about a natural gas power plant, a coal power plant, a nuclear power plant, a wind turbine, it's all about spinning. It's all about spinning a magnet or spinning a wire in a magnet, and they're achieved, right, in really sort of different ways. But as long as you're doing that, you can produce electricity. So the first one we'll talk about is a turbine. And so a turbine extracts energy from fluid flow. There are these sort of two different turbines that I'm showing here that are commonly used in steam turbines, gas turbines. You also have water turbines and wind turbines, which are slightly different. But almost all electricity, again, besides something like getting it from solar, is produced from a turbine. In this case, the turbine looks like this if you were looking at it sort of head on, and it would look like this if you are looking at it from a side angle. And the way this works is that the red part is the part that's moving. You have your fluid flow, either it could be liquid or gaseous, flowing through the nozzles, and it basically hits the turbine and then flows out, and that causes that to spin. And there are two components. So the green components are the stators, which are the parts that are fixed, and then the red ones are the rotors, which are the parts that are moving. In a reaction turbine, it's fairly similar, where essentially you have kind of a steeper angle, and the rotation is slightly different. But again, the main point here is that we are taking advantage of kinetic and mechanical energy in order to spin something. And as long as we can get something to spin, we can produce electricity. Okay. So this is a modern day steam turbine. the way that this is sort of physically constructed is that you have multiple stages of these blades that allow you to capture the flow of the fluid as much as possible. Sort of one way, like I like to think about this qualitatively, if you ever had those like handheld toy fans that you kind of blow into to make them spin, you can hold your hand behind that fan, and what you'll notice is that there's actually still, you know, air coming out of that fan, which means that the air that you're kind of blowing in isn't entirely captured. So if you sort of align multiple of those sort of toy fans up in series, you could see that, you know, the ones in the back progressively spin a little bit slower because they're capturing a sort of a used up airflow. And that's kind of like the principle that's happening here, is that as they spin the blades or spin the rotors, that airflow, you know, drops in pressure and speed, but you're still able to capture some of it. And so these have been engineered to basically extract the maximum amount of work as possible from your fluid flow. So the way that steam turbines work, you have your combustion of your fuel that will heat up water in a boiler. And the water in there will reach extremely high temperatures and pressure, and it will get sent through your steam turbine. Okay, and then what comes out at the end is much lower pressure and temperature water, which then, and I should actually just say steam. It's not in a liquid form, it's in a gaseous form. It gets sent through a condenser where the water collects and is sent back back into the boiler to heat up again in the combustion cycle. And so that that water is actually in this closed loop, and I'll show a diagram of that in a moment. And so this particular type of cycle is known as a Rankine cycle. You can get a sort of maximum theoretical efficiency of a little over 60%, but modern day coal plants are nowhere near that. I think the sort of highest we've ever seen in a real sort of coal plant is a little bit more than 40%, which is actually extraordinarily high. You know, that the average is going to be probably between 30 to 40% efficient. Yeah, and so don't worry about this diagram. This is one of the energy diagrams for going through the Rankine cycle. But mainly, you know, understand this process for how the fuel basically translates the heat into your turbine spinning. Okay, and so to kind of sum up that sort of life cycle, right? So you get your coal. This is a typical example of a coal plant which operates with steam. You get your coal through your mill. It gets combusted in a furnace, and you have this sort of this representation of a water pipe which will send steam through the turbine, which will spin to produce power through your generator. Okay, and so if you've ever seen a coal plant in person or pictures of it, oftentimes you'll notice that there are these towers with a bunch of like vapor or smoke coming out of it, right? And so there are actually two sets of towers with emissions. One is a chimney stack, and these stacks are going to be a lot taller, and they contain a lot of the filter technologies that will reduce the byproducts of emission. And also they are set to a certain height so that the dispersion of the pollutants will be at an acceptable sort of level of concentration once it reaches ground level. So you don't want to be breathing the stuff coming out of the really tall towers. In the smaller towers that are lower and closer to the ground, that is just water vapor. And so that is, perfectly fine to, well, mostly fine to breathe it. It's not really considered a pollutant, right? It's just steam coming out. And I was mentioning that the water flowing through the Rankine cycle is actually in a closed loop. And so the water coming out of the cooling towers is actually through a separate system. And so you've got cooler water that flows into the plant. That's oftentimes coming from like a river source, which is why a lot of these power plants are built near bodies of water. And that water will essentially cool down the water in the closed circuit and then evaporate. And so none of the water coming out of the cooling tower is directly associated with the water that's passing through your turbine. And that's actually a kind of a clever way of doing it, right? Because you can use pretty unpurified water for the cooling part, whereas you wouldn't want to do that for sending water through the turbine, because you could get buildup of impurities within the turbine. But in this case, it's just cooling down the water that's being used directly in the steam cycle. All right. A gas turbine for natural gas is actually quite a bit different. It's not actually using steam in the turbine. It's using the natural gas itself. And so you have a couple sort of main components in a gas turbine. So the first part is a gas compressor. And so what that does, you can imagine kind of a series of fans that essentially, as you pass through the fans, the air will get compressed so that you're at a much higher pressure and higher speed as it moves through the turbine. The second piece is a turbine on the same shaft that's downstream of that. And that is getting spun by essentially the hot gas. So you, in between the upstream and downstream components of your turbine, you have a combustion chamber. And so you are essentially combusting the natural gas within the turbine, and that causes, as it moves through the turbine and the downstream, the rotors to spin. And so you're getting a lot of energy basically from the combustion of the natural gas, which leads to this high heat and pressure from the byproducts of the combustion. The types of gas turbines are fairly uniform in design. In fact, you know, the turbines that you see actually on airplane wings are essentially the same thing as the turbines being used in power plants. You could, in fact, take one off the aircraft and stick it into a power plant and basically be able to get the same results. I probably wouldn't recommend you do the reverse, where you take up a non-aircraft turbine and stick it on an airplane. But in sort of general operation, they're going to be pretty much the same. So gas turbines operate in much the so the thermodynamic cycle is known as a Brayton cycle. This is essentially, again, the diagram of what this looks like with your pressure and volume diagram and sort of heat and temperature diagram. And in practice, the efficiencies are actually quite a bit higher than in coal plants. You're getting around a little lower than 50%. And so this kind of mimics what I was showing before, but in this actual cyclical state where you can see air coming into the compressor, fuel getting injected, combustion happening, and then you're getting the work out of the turbine spinning on the downstream side of the turbine, and then you have exhaust gases. Okay, and so there is one sort of notable thing about this cycle, which is that you are exploiting sort of this combustion process to extract the work in the turbine, but out of the turbine, right? Even though you've captured the energy from the velocity and pressure, but those gases are actually still coming out extremely hot, and so you can take advantage of this. And so natural gas plants, there are kind of two classic types that we talk about. One is a single cycle combustion turbine, which is exactly just this process here. And then you also have a combined cycle. And so I can actually take the hot exhaust gases from the Brayton cycle and use it in a Rankine cycle. In other words, I'm going to take advantage of the fact that the exhaust gases are really hot and then put that into heating a boiler. And that boiler can then operate a steam turbine similar in a similar manner as, you know, a coal or a nuclear power plant would do. And so in this case, you've got your Brayton cycle, Brayton cycle up here with the gas turbine, and your hot exhaust gases are then heating up the water in this system to send steam through your steam turbine, and then you've got the similar system with the condenser here and then cycling through. And so in this way, you've got two different turbines that are sort of maximally extracting energy from the combustion of natural gas. And so in this case, the efficiency of the overall system can be as high as 60%. And so that's like that's almost double the efficiency of your coal plant. Okay, so this is a simple diagram of a combined cycle power plant. Here we have both the gas turbine here with your generator, and then that's connected to a steam turbine. So actually, it's pretty interesting. I don't know if any of you have ever been to a natural gas power plant before, but it actually looks a lot like this. And oftentimes it's in these I mean, it's in an enclosed space, but it's not like in a fancy building or anything. Oftentimes it's like a very sort of simple, like 4-wall operation. Yeah, a lot of these things just kind of look like skeleton structures built around the turbines. Yeah, and they're very, very, very loud. If you ever go visit one, I would highly recommend packing some earplugs, because the turbines in operation are very, yeah, very loud. Okay, so why don't we stop here and take a break for 5 minutes, and I will take any questions in the meantime. I know we went through the material fairly quickly, so yeah, definitely feel free to ask any questions in our break.
Alan, quick question.
Yep.
Would you be able to share a link to the paper you were mentioning, the one that between fracking being more emission intensive than coal? Because I was just thinking, I mean, between the argument of clean coal and fracking, etc., what the trade-offs look like.
Yeah, let me see if I can find it. What was the professor's name? I think it was Bob Howarth. Let's see. Yes, here it is. I remember why this paper was very controversial. So I'm putting it in the chat. I guess I'll pull it up over here too. The name of this paper is "Should Fracking Stop?"
Okay. Thank you. Yeah.
Yeah, extracting gas from shale increases availability, but health and environmental risks might be too high. And there was a big. It's actually kind of interesting. This professor, like, he's not really in the field of like electric power generation or anything like that, or in the sort of broader energy field. He's actually I think he's a soil scientist. And there was a lot of backlash in this paper. I actually remember a lot of my advisors kind of, when I was in grad school, kind of naysaying a lot of the results out of this paper. But I do think it brought a lot of attention to the issue, which was, I think, a good thing. Actually, let me see if I can find, there was so much like outcry over this paper. I remember there was a response paper published in I think PNAS from like 100 authors or something who were basically yelling at this guy. Let me see if I can find it.
But it's definitely an interesting debate. And
yeah, this is if anyone's familiar with oh, what's his name? The Mark Jacobson from Stanford, who published this paper about 100% wind, water, solar, electricity generation. That also resulted in a lot of controversy. This is kind of like on the same sort of magnitude as that. Yeah, I don't know. I think my opinion of the paper is that probably not so accurate, but the fact that it like resulted in a lot of engaging discourse on the issue, I probably view it more favorably than a lot of other academics. Okay, any other questions, concerns, topics of interest? Nope. All right, we'll continue onwards then. Okay, let's see. Okay. This plot always gets messed up on my Windows computers for some reason, but that's all right. This is a plot of power producers on the electricity grid in the United States. The color denotes the fuel type, and the size of the dot denotes the capacity of the generator, or essentially the size of the power plant. And yeah, it's pretty interesting. You'll notice there are some sort of big correlations with field types and geographies. You'll notice on the West Coast, a lot more pink, which is solar. And you'll notice specifically in California, you don't have any blue dots, which represent coal. And so you see a lot more blue in the sort of eastern half of the United States. I should actually, this plot is probably a couple years old now at this point, and I probably should update it, but the general trend is that you're going to see fewer coal plants as they get mothballed and retired compared to natural gas plants, which are sort of popping up all over the place. So in terms of fossil fuel units, you're mainly talking about natural gas in California. The Pacific Northwest has huge resources in hydro, and so those green dots that you see, there's a lot more of that available in sort of Northern California, and especially in Washington and Oregon areas. Yeah, so I know we're mainly supposed to be focusing on the fossil fuels, but also notice some of the other renewable resources available. So in the Midwest is where you have a lot of wind farms, and so you can see sort of splatters of gray in this area. And then lastly, kind of wanted to point out nuclear power plants, which are in orange. So you can see most of them sort of scattered on the East Coast as well. There is one nuclear power plant in California still in operation near San Luis Obispo. That's the Diablo nuclear power plant. It's the last one, and it's going to be decommissioned in 2024 or 2025, end of 2024, I think. And after that, we will be sort of nuclear free in California, for good or for bad. Okay, and so the trend in generation capacity construction looks something like this. So this is over the last century or so, all the way through 2016. And you can see construction. Initially, you had a lot of petroleum plants. That's real bad stuff, where you're combusting oil. And actually, I think back in those days, it was fairly unrefined oil. So, the byproducts of combustion were pretty terrible. And then starting in the 50s, we saw construction of a lot of coal plants. And so coal plants have been around for quite a long time. And that's actually one of the, some of the important decision-making points for transitions. So the average lifespan of a typical coal plant should be something around 30 to 40 years. And so if you're talking about starting construction, especially in the 60s and 70s of lots of coal plants, the 2000s and 2010s is right around when, coal plants are sort of officially set to retire. However, lots of plants kind of drag on their lifetime through, retrofits and sort of in new installed technologies over time and upgrades. And so a lot of the times you end up with coal plants that last for quite a bit longer. But as the prices for natural gas really started to fall, that really sort of changed the economics on whether or not it was worth doing upgrades and worth doing retrofits. And because of that, we saw a sort of really vast amount of coal retirements in the last 10 years. Nuclear power really started around the 1970s, and we'll talk more about nuclear next lecture. But one of the things that you'll notice is that past 1990, the construction of new nuclear plants really sort of hasn't happened, and there are a plethora of reasons for that. Some of that is driven by the economics, some of it is driven by policy, but there's been a pretty big sort of decline in nuclear generation. Natural gas, that has seen a really big boom, especially as prices have gone down, as I mentioned before, and as fracking sort of entered the sphere of technologies. And then lastly, you can see renewables in solar and wind, that's green and yellow respectively, growing pretty rapidly over the last couple of years. And so, we do talk about, the provision of power were, I think I showed a diagram in last class coming from different fuel sources. And yeah, I don't think we need to like necessarily disparage the fact that power generation from wind and solar is really low, because if you actually look at you know, this chart, you can see that the relative growth of those technologies has been like really rapid over the last decade. So I think we're on the right trajectory. Whether or not it's fast enough, you know, we'll talk about that a little bit more later on. Yeah, and so in terms of generation by type, you can see that in terms of the total amount of power that has sort of continuously been trending upwards, and you can see sort of the mix and breakdown of generation in this diagram. Okay. So basic layout of the grid. You've got your power generators, and so how does the electricity actually get to your home? The basic layout looks something like this. So from the power station, you go through a transmission and distribution system. The transmission operates at very high voltages in order to transmit at a in a way such that you're kind of minimizing losses in the transmission. And so those voltages can be in the hundreds and thousands of volts. So that's not something that you want to mess around with. And as it gets closer to the end destination, you will get to substations that will reduce the voltages closer to levels that that you see sort of in the neighborhood. So the way I kind of generally like to characterize is, you know, the sort of really big metal towers that you see, you know, especially when you're like driving along the freeway, that's all part of the transmission system. And then when you're kind of driving around town and you see lines coming on those wooden poles, that is part of the distribution system. And so the place where the voltages get either stepped up or stepped down are at substations. So for the folks who are currently in Davis, if you want to see the substation, it's over the local substation for the city of Davis is over on what street is that? It's like on Third and L, I believe. It's the street that like runs all the way down to Target. And so if you kind of like peek over the wall in there, you'll see a bunch of these like really big transformers that are reducing the voltage for electricity coming from the transmission system. So then that electricity will get connected into your end users, either commercial and industrial, where you may actually even have higher voltage than in residential, depending on what they need it for and what they're doing. But by the time, you know, it gets to the plug coming out of your wall, you've gone all the way down from you know, as high as 300,000 volts down to a 110 volt in the outlets. Okay, so actually at this point, I usually have a little game to play, but unfortunately I wasn't able to work out a good way to do this online. So unfortunately we're gonna have to learn about power dispatch in a more sort of boring way. But so when I look at this sort of diagram and I think about, you know, residential customers using power, let me actually go back to, I'm going too far. This diagram. So let's say I'm living here in Davis, and I decide to turn on my computer or turn on the TV. That requires some electricity to be, to go into my end product or end use. And so one sort of interesting factor about the electricity system is that the power essentially has to be used as soon as it's generated. So yes, okay, there you do have storage devices and that sort of thing, but sort of generally, when I flip on a light switch, or if I turn on a TV, or I start my microwave, some power plant somewhere is like ramping up its operation slightly in order to be able to ensure that the electricity is flowing, and that they can like balance everything in the system. And we won't get into all of the like electrical engineering details that go behind that, but basically, when the load is there, something has to ramp up or turn on. And so the question is, okay, what power plants are turning on, right? Like if I look to this area right here, is it this natural gas plant or this natural gas plant or maybe one of these hydro facilities turning on? Like who gets to decide which power plant is essentially being dispatched to react to any sort of power needs? And the answer to that is that the order in which power plants are dispatched is controlled by a system operator. And so in California, for most of California, that is an entity known as CAISO, the California Independent System Operator, so the ISO. And like with what criteria are power plants dispatched? It's actually almost entirely through an economic system, a bidding system, in which a power plant will essentially say, okay, I will bid X dollars or Y dollars, which means that at a certain bid level, once you reach a bid level, everything below that will essentially get turned on. And in this case, the point of the game that we would have played is basically to figure out a strategy in which to maximize your revenues as a power producer. Long story short, the way in which you do this is you bid the marginal cost of the fuel to produce the power. In other words, if as a natural gas producer, if it costs me, $10 to produce 1 unit of electricity, I will bid exactly $10. If I'm a renewable source and it costs me nothing, then I will bid $0. And so what happens is all these power plants will put in bids, right? And so you build what's known as a dispatch curve, which is you order the power plants sort of one by one based on how much they're bidding from lowest cost to highest cost. And what ends up happening is you basically turn all the power plants on up till the last amount that you need. And whatever bid that last person had is what everyone gets paid. And so your strategy is like, okay, if I bid exactly the cost of my fuel, then at the worst, I will break even, right? But but if I am not the last person on the dispatch order, then I can make a ton of money, or some money, right, in profit. And so that is basically describes the sort of economic operation of the order in which power plants turn on. And there's all this kind of like strategy to this, right? In terms of developing new resources and new capacity, right? Because now you have to think about how often you're going to turn on relative to other people and what you think the like future price of fuels can be, and that can be pretty complex. There's one edge case which I always try to pull out in the game that we play, which is what happens if you have to turn everyone on. Basically, if the load is so high that every generator in the system gets turned on, or maybe I'll put it this way, like the sort of most extreme generators have to turn on. So this is actually a phenomenon that occurs because like electricity demand is not uniform throughout the entire year. You can on certain days have like a really high like AC load if it's really hot. You guys may recall, for those of you who are in California, some of those like flex your power type calls, and even recently where they were saying, hey, like don't turn on your AC until some amount of time because you're putting stress on the grid, and turning on a lot of these generators. And so from an economic perspective, there's a pretty interesting thing that can happen. If I'm the last generator and I know that you have to turn me on because I'm like your last resource, well, I'm not going to bid the my marginal cost because I know that I'm needed. So instead, I'm just going to bid like, you know, $1 million per unit of electricity or something, and I'm going to get a really fat payout. And that's because the sort of the last guy on the dispatch curve can kind of take advantage of this. And so there are actually a couple like crazy generators in the US that operate profitably by turning on like once a year, and they just have like ridiculous bid prices. And oftentimes those are like these really terrible, like expensive, like oil plants, something like that. And there are kind of some safeguards around that. So oftentimes system operators will have ceilings on bid prices to prevent gaming it too much. But to a degree, you know, some of it is necessary because you will inevitably have generators that don't operate very much, and so they need sort of really high margins in order to stay in operation for when you need them. Okay, let's go back. Let's talk about some environmental impacts. So the whole point of carbon cycle and thinking about climate change is that, okay, you actually have a pretty large flux of carbon sort of occurring naturally. So from non-anthropogenic sources, you have respiration, photosynthesis, you have ocean exchange, and these things are leading to sort of a net exchange of carbon sinks and carbon releases into the atmosphere every year. And sort of the main problem is that once you add on anthropogenic sources for carbon emissions, those fluxes are no longer in balance. And so you get an excess of CO2 sort of back when I was like first learning about this, the rough sort of back of the envelope or you know, simple numbers that we had in our head was about 20 gigatons of carbon annually, balanced sort of naturally, and then essentially an equal amount sort of being emitted into the atmosphere. And I think those numbers are probably a little different now, but the general idea is on those sort of order of magnitude scale, you're talking about anthropogenic emissions about equaling the total sort of natural emissions happening from non-anthropogenic sources annually. Okay, and sort of drawing focus back to the emissions from fossil fuels. This is kind of what it looks like over the last couple decades. And as I mentioned before, and here we can really highlight this, right? So coal energy consumption has really been replaced by natural gas at nearly a sort of 1-to-1 scale in the last decade. And that has led to a really sort of stark decrease in coal emissions. And the sort of rough order of magnitude for emissions rates from power production in coal versus natural gas. As I mentioned, natural gas is about half. So if you wanted like a rough number, it's about 1,000, oh man, is it pounds or kilograms? I'm gonna be off by a factor of 2. I think it's 1,000 pounds of CO2 per megawatt hour for coal, and roughly half that for natural gas, about 500 pounds per megawatt hour. And yeah, sorry, I don't have it quite straight. It's either pounds or kilograms, and I'll check that and get back to everyone. But because it's half the amount, when in a 1-to-1 replacement, we've seen a sort of decrease in coal emissions by 700 million tons, and natural gas emissions has increased by 300 million tons annually. So you're talking about displacing about 400 million tons annually, which is really quite an astronomical amount relative. Like, it's not astronomical in the sense of like, that's how much we need to be reducing for like our climate change goals. It really is, even that is probably too slow, but relative to any sort of policy that has, at least in the United States, that has kind of pushed for climate change mitigation, this far and away has led to the largest reduction. So fracking, yeah, at the end of the day, has been pretty beneficial from a climate change perspective. And these days, you know, this graph goes out to 2015, but this trend has continued. In 2014, the Obama administration passed this pretty landmark policy called the Clean Power Plan. And that was a federal policy affecting sort of state-by-state levels of power plant emissions that really would have kind of forced coal power into retirement fairly aggressively, because the like stringency with which the emission rates were happening basically meant that coal power had to get super clean or basically had to retire, and it would be fairly uneconomical for a lot of those power plants to continue operation. And I think that transition really would lead to the similar sorts of decreases. There are some critics who who say that, and probably it was probably true that a lot of those decreases were going to happen anyways because of the price differences. But either way, the clean power plan ended up getting shelved with the Trump administration. It was challenged a bunch in court by a number of states, and the Trump EPA kind of took that opportunity to essentially get rid of it. But you know, hopefully with the new administration, that specific policy or a similar type of policy is likely going to be implemented in sort of the near future. And so I would definitely expect this trend to continue, and that coal power is really kind of going to rapidly decrease as we transition into more natural gas resources. Okay, and so I think that about covers it for today. That's the last slide that I have, where we've covered basically everything from, you know, the fuel extraction and acquisition all the way to impacts from environmental downstream of combustion. Yeah, and so at this point, I'll do kind of the same thing as before. If people have any like comments or questions or want to discuss anything, happy to chat more. And I'll stick around for 5 or 10 minutes. Otherwise, I guess I'll see you guys on Monday for the next lecture, and that's when the first homework will be assigned as well. So we'll end a little bit earlier today.
Oh, excuse me.
Yep.
Yeah.